Have you ever wondered why we don't have powerful quantum computers on our desks yet? The answer usually comes down to one specific, frustrating number: coherence time. To understand it, I want you to imagine a coin spinning on a table. While that coin is spinning, it's a blur. It's not heads, and it's not tails, it's kind of both at the same time. In quantum mechanics, we call this superposition. But we all know what happens next. Gravity and friction kick in. The coin starts to wobble, it loses its balance, and eventually, slap, it falls flat as either heads or tails. Coherence time is simply a measurement of how long that coin can spin before it crashes. In a quantum computer, our coins are qubits, and they are incredibly fragile. If a qubit is spinning, meaning it's in a valid calculation state, it is coherent. But the moment heat, a stray magnetic field, or even a tiny vibration hits it, the qubit loses that state. It crashes. We call this decoherence. Here is the catch: you can only perform calculations while the coin is spinning. If your calculation takes 15 seconds to run, but your coherence time is only 10 seconds, your computer will crash before it gives you the answer. The result you get will just be random garbage. This creates a massive engineering challenge. Right now, we have two main types of quantum computers, and they handle time very differently. Think of them as sprinters and marathoners. First, you have the sprinters. These are superconducting qubits, like the ones used by IBM and Google. Their coherence time is super short, only microseconds. They die very quickly, but they are incredibly fast. They can squeeze in thousands of operations in that split second before the qubit crashes. Then, you have the marathoners. These are trapped ion qubits, like those from IonQ. These guys can hold their state for seconds or even minutes. That is an eternity in the quantum world. The downside: they are much slower at doing the actual math. So it's a trade-off. Do you want speed or do you want endurance? So when you hear researchers talking about improving T1 times or fixing dephasing, they are just trying to keep that coin spinning a little bit longer. The ultimate goal is something called quantum error correction. Basically, using software to flick the coin and keep it spinning indefinitely. Once we crack that, everything changes. I hope that clears up one of the biggest bottlenecks in tech today. If you found this explanation helpful, make sure to hit that like button and subscribe for more deep dives into generative AI and quantum concepts. See you in the next video.